Hey everybody, this is Alex Merced, and welcome to this 8-bit version of my Apache Iceberg 101 presentation, 2026 edition. So it's going to cover a lot of the newer Iceberg bits and bobs. If you guys enjoy learning about Iceberg, do watch this presentation. Now again, who am I? I'm Alex Merced. I'm head of DevRel over there at a company called Dremio. If you haven't used Dremio yet, head over to dremio.com and try out the free trial. You'll be happy that you did, especially after this presentation. But bottom line is just a little bit about my history here in the Iceberg space. I've been a evangelist for, well, I'm in the head of DevRel now, but I was an evangelist for Dremio for the last 4.5 years. Basically, my role here has been one, helping educate people about open source technologies like Apache Iceberg, Apache Polaris, Apache Arrow, helping people get hands on, doing workshops, all sorts of good stuff. And in that, I've gone to write some books on the topic, such as Apache Iceberg, the Definitive Guide, Apache Polaris, the Definitive Guide, and my newest book, Architecting an Apache Iceberg Lakehouse, which will be releasing May 19th on Amazon. But you can pre-order now over there. So the first two books I did with O'Reilly, and this is the next book I did with Manning. But yeah, so basically, I've spent a lot of time thinking about Apache Iceberg and writing about Apache Iceberg. So bottom line, let's just talk a little bit about the problems that Apache Iceberg was trying to solve. Because if you don't understand the history of it, it's kind of hard to appreciate why we're here. So this all started in the company called Netflix. You might have heard of, okay, if you like to watch movies. And what happened is that Netflix was using sort of what's nowadays would oftentimes be thought of as a legacy technology, even though when you really think about it, most of these technologies that people talk about nowadays weren't created that long ago. Things are just moving really fast. But a technology called Hadoop, which is a distributed storage system. So it's a way of basically tying up a bunch of lower powered computers to treat them like a big hard drive. And in Hive, which was a way of tracking originally was mainly a way of taking SQL so that way you can do analytics on Hadoop, but also developed what's called Metastore, which was a way of tracking information you had on your Hadoop cluster. And these became sort of industry staples, but they had lots of bottlenecks because the idea was when you were using this Hadoop thing, this like sort of again using it all these computers as a big hard drive, this pattern was known as a data lake, and the data lake was a response to the data warehouse. And the data warehouse, all that was is a database that was optimized for analytics. The problem is these data warehouses were expensive. They could only handle your structured data. So bottom line is people needed a place where they could store data they didn't want to have to pay too much for, but when it was structured, and unstructured data they couldn't store in the data warehouse at all. So thus the development of like Hadoop and Hive and the data lake paradigm. But again, the data lake, treating your data as a bunch of files on a storage system, wasn't necessarily as pleasant as treating your data as a bunch of tables in a data warehouse. If you've ever worked like in an office where people are emailing themselves each other files and you're not sure which is the right version of a file to use or to do whatever you need to do for business, that's the kind of situation you'd end up. You just end up no one knew where the right stuff was, whether it was updated correctly. These are the kind of issues you had with the data lake. And again, with the data warehouse, it was a much more pleasant experience, but it was also really expensive, and you couldn't really store everything there. So the goal was, how could we make the data lake not turn into a data swamp, but became more like a data warehouse, so become a data lake house. And basically what you needed to solve was, one, the speed trap. So basically this had to do with sort of the way you would have to determine which files to scan. It was very expensive. It required a lot of file listing. And then also how do you maintain consistency and asset guarantees to make sure that everyone's on the same page as what is the data, and then when you update the data that you can do it safely. So how do you solve the answers to these problems? Well, this is where Iceberg comes in. And again, it's trying to solve lots of different problems. So not just the problems I just mentioned, but also problems, again, we mentioned asset transactions, the ability to update the table, to evolve the table. You take for granted that in databases and data warehouses, I could just add a column to a table or update the type of a column without much effort. But that was not the case on a data lake, because again, it's not the same kind of system. You're just talking about files on storage. So how do we bring evolution to our tables, so where we can update the way our tables are structured without having to rewrite the whole table? And two, how can we handle partitioning better? Because there's a bunch of partitioning pains with Hive that would result in consistency issues if something got placed into the wrong folder, or having to write complex queries so you can avoid full table scans. And these things were not very pleasurable either. So the idea is like, hey, we want to get rid of all these sort of things we don't like about the current thing. So with that, they built Apache Iceberg. So a team of engineers over there at Netflix, including Ryan Blue and Daniel Weeks, built Apache Iceberg. And this is essentially what it is it's not a piece of software that you install. So it's not like, hey, I install Iceberg and now I got Iceberg. What it is, it's a specification. It's how you write the metadata around a table or around your data. Now, what is data? Metadata? It's just data about the data. Okay, but the cool thing about having data about the data, it makes things easier. It's like a map. A map is essentially metadata. The map isn't the place I want to go, but it gives me information about places for me to better figure out how to go. Okay, taking the extra step of reading the map before I get into my car. Nowadays, we have GPS, but theoretically, think about the days we would use maps. Taking a moment to look at the map will save me lots of time versus me just driving around aimlessly trying to find the location that I'm trying to look for. And that's sort of the purpose of the Apache Iceberg metadata standard. So the idea is, hey, we write all this extra data around the data that you have on your data lake. Engines and tools that are trying to work with your data don't have to wander around aimlessly. They can intelligently and quickly get to where they're going. Cool. Now, the thing is that once you create a standard, a specification, you need to help people follow that specification, because it only works if everyone follows the same rule book. So in order to help people do that, they would create libraries in Java, Python, Rust, and Go. And these libraries would help engines be able to use the standard and use it in a uniform way. Okay, because the problem is if everyone implemented the specification on their own, everyone might implement it slightly differently, and then you end up having all sorts of different issues where the metadata isn't perfectly usable across different tools. And again, another problem that this was solving, or ended up solving vicariously, was creating interoperability. So now these Iceberg tables can be used by any tool that you want. All they have to do is understand the Iceberg standard, but then by adopting that Iceberg standard, you fix all those other problems I mentioned with partitioning, with performance, with consistency, etc. All that stuff just is better. Now, the Iceberg standard, the specification, has evolved over the years. Okay, again, it's a standard, and it's an open standard, which means everyone gets to pitch in and express their opinions on sort of where the standard should go. So there's generally a team of engineers you can sign up for the mailing list if you want, and you can participate in the mailing list if you want, that discuss sort of what direction of what features should be added, how those features should be implemented, how the spec should look like for those corresponding features, etc. And basically, very once in a while, there's a new version of the specification gets released. So the first version of specification just kind of handled the primary read and write to the metadata, mainly for batch purposes. So essentially, the assumption was that maybe you're updating the table once a week or once a day. So using a typical sort of copy on write style of updating the table, which means, hey, if there's a file and I'm updating one record in a file of 10,000, I'm just going to rewrite the file with the update. So I'm rewriting all 10,000 records. That's copy on write. That's better because there's less work when you eventually later read the table. But again, you're writing a lot more data when you write to the table. And that was the only option in V1. Okay, I could read and write to an Iceberg table. It was copy and write. It worked. But there are a lot of people who update the table quite frequently. And when they update the table frequently, they're not just adding table, they're not just appending data, they are making small little updates. Okay, they're updating a couple rows here, upserts. Okay, so they're updating data, they are deleting data. And Iceberg wasn't built for this yet. So in version 2, they added the ability to kind of handle these types of use cases. So row level deletes, it created a thing called delete files that would be able to track what was deleted without you having to rewrite the whole file. And that allowed those types of use cases to work better. Now, V3 tried to address many different issues that were, basically as people use Iceberg more and more, you start finding edges. So each of these iterations tried to address sort of the biggest edges that are going there at the time. And one was like a lack of support for nanosecond timestamps. So V3 added that. So now you can have much more fine-grained timestamps. Row lineage tracking, so you can track sort of the changes to rows over time. High performance binary deletion vectors, so we move away from delete files, having all these different files that track what was deleted for these row level updates, which would add a lot of files you'd have to read, and moving towards, instead of just putting all that information in a single binary blob, stored in a specific type of file for Iceberg tables called puffin files. I won't spend too much time on puffin files, but just know it's another standard within the standard for how you write these files that have binary blobs. Extra information. Added the variant data type, which basically allows you to handle JSON data in a much faster way. So all this stuff came in V3, and there's already lots of talk about what's going to be in V4, such as single file commits, moving metadata over to storing them as Parquet files versus Avril files, lots of other really cool discussions. But again, I wouldn't expect V4 to be ratified until 2027. And then probably, you would expect support for it within the tooling broadly, not till 2028. So basically, now you're starting to see the point where most tools have V3 support. So now we're just kind of getting to a point where people can begin using V3 tables and start moving away from V2. Now, when we think about the metadata standard as it currently stands, essentially this is kind of what it looks like. So generally, starting from the top, okay, level 1, you start with a catalog. A catalog is essentially just is a heart of your lakehouse. It's a thing that tracks all the things that are in your lakehouse and who has access to them. It's your flight traffic controller. So essentially what would happen is that an engine, let's say like a Dremio, would say, hey, I want to run a query on the sales table. It would go to the catalog and say, hey, catalog, where's the sales table? And at first, the catalog would say, hey, do you have access to the sales table? And if you do, it would then give you a location wherever that data is stored, specifically a file called metadata.json. Now think of the metadata.json as like your business card, okay? Like when I have a business card, it tells you sort of who I am, what's my role, how you can contact me. It's not all the information, but enough information that you can dig deeper. Okay, you might find my website or something like that, and then you can find more information. So that is what the metadata.json is. It's the business card of the table. It tells you all the basic information you need to proceed further, such as, what is the table? The history of snapshots, the history of the table schema, the current schema of the table, etc. Now, what this will do is going to point you to a index of what's inside a particular snapshot. So every snapshot gets a manifest list. It's a list of manifests, essentially. So, okay, now, to better understand that, we need to know what a manifest is. So right now I'm going to skip all the way to the bottom to the actual files, okay, the individual files on your data lake that actually have the data. So you're going to have a bunch of Parquet files that actually have the data. So essentially what happens is that if you're not familiar with Parquet files, they're a file format that's really good for storing analytical data, and they generally have metadata themselves. So every Parquet file has metadata that tells you, one, what's inside the file, what's are inside chunks of the file called row groups, allowing you to scan in the same way that the metadata helps you scan an Iceberg table. The Parquet's metadata lets you scan that Parquet file very intelligently. So it's kind of like having a map of a subsection of the map. Now, back in the day, one of the things that took so long is that if you had a table that was made, or a data set that was made up of 100,000 Parquet files, while you could scan each of those individual Parquet files intelligently, you'd still have to open up each Parquet file to read that metadata to see if you need to go any further. So with Iceberg, we take all the data files that are part of the table, and we summarize them in a manifest. So there's going to be more than one manifest. So each manifest will cover a group of files. Say, okay, hey, this manifest is going to list this 1,000 files. This manifest is going to list this 1,000 files, along with the summaries of those files. So basically, like this Parquet file has values between this and this for these columns, and so forth. It has this many records, this many nulls. Basically, the general summary of each file. So the manifest is a summary of a group of files, but there's more than just a particular version of the table might include more than one manifest. That's why you need a manifest list. It's saying, okay, hey, for this version of the table, you can find the files for this version of the table among these different manifests. And then we would then summarize the stats for that manifest there, saying, okay, hey, this manifest covers these range of values, etc. Essentially, you're rolling up statistics from the original Parquet files up to the manifest level, and then rolling up so those statistics up to the manifest list level. And the cool thing about that is by having those statistics in these files is that now, instead of having to read every Parquet file, I have a summary of those statistics that I can use to begin skipping Parquet files. So I can first take the manifest list, look at the metadata in there, and say, hey, can I skip any manifests? So I just don't have to read them? So you can skip chunks of manifests, typically based on partitioning. So basically you're saying different, I can say, hey, nothing in this particular manifest has data in the partitions that I'm looking at. Then when I take a look at the manifest, which has the individual files, I can be like, okay, hey, out of 1,000 files listed in this manifest, there's only like 2 files that I need. So instead of having to scan all 100,000 files, when you get to the end, I may only have to scan a fraction of them. And this is why you're able to result in much faster queries and query execution and scan planning than you would before Iceberg. Okay, this is sort of this way this metadata is structured is what allows Iceberg to be so fast for those who fully take advantage of the metadata. So again, you have the metadata files that sort of track the high level of the table. So again, what is the snapshots, what is the table schema, etc. You have the manifest list, which lists all the individual manifests, allowing you to determine, hey, do I need this manifest? Yes or no. Then you have those individual manifests, which list the individual files, allowing you to parse out the individual files. That also will, at this point is when you would leverage the deletion vectors in the Puffin file to figure out, hey, are there any records among these files I should ignore because they were deleted previously? All that information would be there. Cool, but as I mentioned at the top, there's a catalog. And the problem with catalogs is that catalog is another piece of software. It's some sort of system. Before, when Iceberg was originally created, there wasn't many options. People would use like Hive, or they would use like a database. There wasn't, so the thought process, or it wasn't anticipated that there would suddenly be a world where there's like now dozens of different catalogs you can use with Iceberg, and all of them work differently. So as that world became more obvious that it was coming, in order to avoid the frictions that were starting to show up, the Iceberg project came up not just with a table standard, but with a catalog standard. So this isn't a standard way to build a catalog, it's a standard way to talk to a catalog. So for example, people are going to build catalogs that work different ways, and that's fine. But there's certain things that you're always going to do when you're working with Iceberg. I might ask for, hey, what's a list of tables that I have in Iceberg? Where's the metadata for this particular table? Can I update this particular table? Can you put into this metadata location instead? So these questions are going to be questions you're going to ask of any catalog. These are standard read-write Iceberg operations. So instead of having every catalog come up with their own API to ask these very standard questions, the Iceberg REST catalog, the REST spec, basically says, build your catalog however you like, but for these standard operations, you need to have an API that has these particular endpoints. And if you have those particular endpoints implemented in your catalog, that means any tool that supports the REST spec can now talk to your catalog. So they don't have to build custom support to support your catalog. Basically, they would just use the existing connectors. Because before, the issue was you had to create a connector for like every catalog. Now, one connector can work for all catalogs because they all talk the same way. So this further enabled interoperability in the market. So now you get interoperability of tables and interoperability of catalogs. So you could use a catalog, use any tool. You can use Iceberg tables with any tool, whether it was Spark, Dremio, Flink, Athena, and many, many more. So that kind of summarized Iceberg as a whole, but a distinction that's going to be mattering more as people becoming more, I would say, more completely start using Iceberg as their main data platform. So instead of moving away from storing their data in any particular data warehouse to just storing their data as Iceberg tables and using different tools for different use cases, I think there becomes it becomes important to understand when something is a tool that supports Iceberg versus a tool that is Iceberg native. Now, what's the difference? A tool that supports Iceberg has the ability to, work with Iceberg tables to some extent, but it's not their primary focus. This is most data warehouse platforms. They generally have their own proprietary format that they've been building for years. Their engine is very optimized for reading that format, so you're not going to necessarily get the same performance on Iceberg, because generally Iceberg is something they kind of added on because customers wanted Iceberg. They don't have the same level of product and engineering resources dedicated to their Iceberg support. Generally still good. Again, because the Iceberg project creates all these libraries, you can get most of the benefits without much work because it's all been provided by open source. But at the same time, again, you're not going to get, it's not their first class thing. It's a thing you can opt into. Okay? Versus something that's Iceberg native, these are platforms that were built for Iceberg. So there is no proprietary format. There is no other thing they do Iceberg. So this would be, for example, would be Dremio, where Dremio's engine is Iceberg first. It reads and writes to Iceberg. It does everything with sort of an Iceberg mentality. It's the product and engineering focus is optimizing how you work with Iceberg to give you the best performance possible on Iceberg. And they're not thinking about anything else. They're not thinking about some other proprietary format. There's just Iceberg. So it's a Iceberg native platform. Dremio has a bunch of other features, but it's primarily an Iceberg query engine more than anything else. Okay, with a built-in catalog, and basically everything is designed around giving you the best Iceberg experience. Versus, again, your traditional data warehouse, which, again, will allow you to read and write to Iceberg, which is, again, depending on what you're trying to do, enough, but they're not giving you, it's not necessarily an Iceberg platform. Like, you won't, if you were to just spin up a particular data warehouse and write a table, you're not writing an Iceberg table. You're writing a table in their native format. So generally, again, it depends what you're trying to do. If you're trying to standardize on Iceberg and really treat Iceberg as your sort of native way you build your analytics platform, you are going to want to use an Iceberg native platforms. Again, primarily that would be Dremio. There are other startups that are newer nowadays that are creating more Iceberg tooling and are focusing on Iceberg. But if you're just someone who's using a traditional data warehouse and you're just trying to offload some of your costs by moving your data to S3, then oftentimes just the extra Iceberg functionality in your traditional platforms will at least serve you in that use case, and at least your data, that data will become interoperable. So again, still worth moving to Iceberg regardless. But over time, as you decide you want to standardize more and more Iceberg, the Iceberg nativeness of the tools you're using, how much do they weigh Iceberg as part of their roadmap, and how they work and develop their engine is going to matter more for developing sort of like what you can and can't do with your Iceberg tables. And again, it doesn't necessarily mean you can't use, the beauty of Iceberg is you have interoperability, so you can use multiple tools. So in this case, like, you could be using X data warehouse. That doesn't mean you have to get rid of X data warehouse, but you may also want to include Dremio as the thing that maintains your lakehouse and handles a lot of the sort of the day-to-day working of your lakehouse because it's built for that. So these are things to think about as you enter the Iceberg world. Now, at this point, you've cleared the stage. Okay, you've done it. You've seen this presentation, so you can start your agentic lakehouse or Iceberg lakehouse journey. Now, one thing you can do is read the books that I've written. Okay, again, Apache Iceberg, the Definitive Guide, Apache Polaris, the Definitive Guide. Those two you could go get for free from Dremio.com. So if you go to Dremio.com, you can find places where you can download a digital copy of both those books for free. If you want to buy physical copies of those or many of the other books I've written, head over to books.alexmerced.com. You'll find a listing of all my writing. Also join the Lakehouse communities, such as the developer.dremio.com community. Even though it's a Dremio community, it is open to anyone who wants to talk Lakehouse, Iceberg, etc., or just part of the data community. The datalakehousehub.com, which is another data lakehouse community that I run, and then there's the official Iceberg Slack community, which you can find over there at iceberg.apache.org. But yeah, keep learning, keep curious. Iceberg is really cool. Again, if you want to just get hands-on with Iceberg really quick, just sign up for a Dremio free trial. You literally can just sign up in a few moments. Just use standard SQL to write a table, and guess what? You have just written your first Iceberg table in moments. So to see how easy it is. Okay, and then again, Dremio has a built-in catalog that you can then connect to other tools like Spark. So you could go create a quick table in Dremio, then connect Spark to that catalog and see that, look, it's interoperable. Along with a lot of other great features that I'm not going to get into right now. But yeah, you guys have a great day. My name is Alex Merced, head of DevRel at Dremio, and see you all later on.